Help in Pharmaceuticals in association with Higher Secondary Principals Forum.
Hello students, today we will going to study very important lesson of our life which is there in 12th also, 12th science. Okay. Now see this slide here, you can see this aeroplane. Now this plane is moving in this direction, this arrow is moving in this direction, this is moving in this direction. So this lesson is basically depend on direction. Direction and it has magnitude. So which lesson is this? It is vectors. So what is vectors? We will see what is vector. Now see, I am standing here, I want to go in this direction, so I will move this side. If I want to move in this direction, I will go this side. If I want to go out from this room, I will go this side. So direction is very, very important in our life, and this direction is related to this lesson, vectors. Now see here, these are the example of vectors. See, in this video we have seen that the two planes are moving and both the planes are parallel planes. Now we are learning in this lesson vectors and scalars. What is the difference between vectors and scalars? Now I am standing here, and if my height is not related to direction, so it is only height, I will get only a single number. That single number is called scalar. If I am moving, then I will have magnitude and direction also, that is called vector. Now see the difference between vector and scalar. A physical quantity that has only magnitude and no direction is called scalar. Physical quantity which has magnitude, there are so many physical quantities which are having only magnitude. For example, mass, length, time, area, speed, density, work, temperature. All these quantities are having only magnitude, no direction. These quantities are called scalar quantities. Whereas velocity, acceleration, force, displacement, all these quantities are having magnitude and direction. These quantities are called vectors. So these are the difference between vectors and scalars. Now see in this, see here the ball is hitting here and it is coming here. So this point is called an initial point. The ball is moving in this direction. It has direction and it has magnitude. Magnitude of this is AB, and it is moving in this direction. It is a vector AB. Now see here this arrow. It starts from here and it goes here. This point is called initial point of a vector, and this point is called terminal point of a vector. The distance between A and B, it is called magnitude of the vector, and it is always denoted by modulus sign because the distance is always positive. Now the vector is starting from A and ending with B. So the initial point is A and the terminal point is B. Now see, this vector is in this direction, this vector is in this direction. Now there are different types of vectors. One is zero vector or null vector. A vector whose initial and terminal point both coincide. See here, the initial point is A and the terminal point is also A. Now for example, I am standing here, I am not moving. If I move like this, I will get one more point B. So point A and point A only, the initial and the terminal point is A. The magnitude is 0 in this case. In case of this zero vector, the magnitude is 0. So this type of vectors are called zero vectors. Point B and it is B only. Starting point and the ending point both coincide. This type of vectors are called null vectors. Now zero vector is always denoted by this 0 on the top of that bar, or it is just lying here. Zero vector has no magnitude. Zero vector is not having magnitude and no definite direction. There is no direction. I am standing here only. I am not going this side, this side, this side. So no direction. So zero vector is not having direction. Next one, unit vector. A vector whose magnitude is unity. The magnitude is 1 unit. It can be 1 centimeter, 1 meter, 1 kilometer. The vector whose magnitude is unity is called unit vector. Along the unit vector along any vector is given by this A cap This cap is denoted for, unit vector is always denoted by cap, and this unit vector is whatever vector upon its magnitude. Next, co-initial vectors. Vectors whose initial point is same. Vector is starting from here, it is going in this direction, one vector. Another vector is going in this direction, another vector is going in this direction, another vector is going in this direction. All these vectors, the initial point is same. This type of vectors are called co-initial vectors. Now for example, from Dabolim airport, one plane is moving towards Dubai, one is Mumbai, one is Bangalore, one is going to Delhi. So the initial point is same. This type of vectors are called co-initial vectors. Collinear vectors. Now just now you had seen in the video, two planes are moving, okay. Two planes are moving like this, okay. So those are parallel vectors. Now see this, it's moving in this direction. The other one is also moving in this direction. Here also it's moving in the opposite direction. This is going this side, this is going this side. This one, the initial point is same, but this one is going this side, one is going this side. So this type of vectors are called collinear vectors. Equal vectors. Two vectors A and B are said to be equal if vector A and B have the same magnitude and same direction. Now suppose these are the two vectors, okay, and they have same, they are moving this way, both are moving this way. So the magnitude, the length of this both are same and the direction is same, then only it is called equal vectors. Now suppose the magnitude is same, but one is going this side, one is going this side, then it is not a vector. This is clear to you? It is not equal vectors. It's not the example of this. For equal vectors, the magnitude has to be same and the direction has to be same. Then these vectors are called equal vectors. Negative of a vector. Okay, vector is starting from A and ending with B. The another vector starting from B and ending with A, but the directions are not same. Okay, now for example from A to B, this is a vector A to B and this is another vector A to B. Okay, now if it is moving from this direction A to B and this another vector is moving in the another direction, same, it is AB and BA, both are not same. Both, if you take like this and if they are moving in the same direction, they are equal because the magnitude and the direction is same. But if it is B to A and A to B, both are not same, their directions are different. A to B is from here and B to A is from here. So both are not equal vectors. One vector is negative of another vector. Triangle law of vector addition. Okay, now see here, one person is here from Andhra. Okay, from Andhra he is traveling to Bangalore and from Bangalore he is traveling to Chennai. So he can travel directly from Andhra to Chennai. So A to B and B to C is same as A to C. So this is called triangle law of vector addition. So Andhra to Bombay and Andhra to Bangalore, Bangalore to Chennai is same as Andhra to Chennai. So A to C is same as A to B plus B to C. This is called triangle law of vector addition. Next one, parallelogram law of vector addition. Now if two vectors are represented in magnitude and direction by two adjacent sides of a parallelogram, see this and this, these are the two vectors, two adjacent sides of a parallelogram, then their sum, this OA plus OB, their sum is given by OC, the diagonal of a parallelogram. The sum of two adjacent sides of a parallelogram and the initial point is same here, then the diagonal, the sum of these two is represented by OC. O to A plus O to B is same as O to C. Why it is like that? Because this vector is same as this vector because both are parallel and they have same magnitude. So by triangle law, O to A to C is same as O to C and these two are same. That's why we are getting parallelogram law of vector addition. Properties of vector addition. In the same way, see here, if you go from here to here, O to A and then A to C, you will reach from O to C. Okay? So, this is vector A bar, this is B bar, this is B bar, that is why this is B bar. Why both are same? Because they are parallel and their magnitude is same. So, both the vectors, this vector is same as this vector. So, A bar plus B bar, if I go from this side, I will get A bar plus B bar. But if I change the direction, if I move from here and then here, okay, this is B bar and this is same as A bar, this both are same, parallel and their magnitude is same. So, this is same as B bar plus A bar, both are same, that is why this thing is commutative, this is commutative. Vector addition is commutative. Second property, now suppose you want to travel from Orissa to Chennai, okay. So, you can travel from Orissa to here, Andhra to Chennai like this. In between you can go here and here also, this part is also there. So, from here to here or here to here, and in between you can go from here to here also, or from this, see the diagonal here, these two are joining, here these two are joining. From O to C, you can go O to B and B to C, okay. So, you can travel here O to A and O to B. O to B is same as O to A to B and then B to C. So, finally from here you have to reach here. There are two ways of going from O to C. This is one way, this is another way, and if you take here A, B, C, then you will get this associative property of vector addition. Multiplication of vector by scalar. Multiplication of vector by scalar. Now see here, suppose this is 2 times A, this vector 2 times A, okay, in this direction. This is one vector, multiplying by 2 means it is double, 2 times A, like this it is, okay, and A is this vector. Half of A will be half of this, suppose it is half of this is this here, okay. So, half of A will be this is A and this is 2 times A, this is 2 times A. All three vectors, see here, they are in the same direction. So, we are multiplying this vector A by scalar, here it is 2, here it is 1 only, here it is half in the same direction. So, these vectors are parallel. Now, same vector 2 times A, you can reverse like this, the direction will change and you will get minus 2 times A, you will get minus 2 times A. Now, same way if you reverse this vector, if the direction is changed, magnitude is same, you will get minus A. This vector, if you change the direction, you will get half of A. So, all these vectors are parallel vectors and we are multiplying the vectors by scalar, then these vectors are parallel to each other. Now, see this point 2, 4 I am taking in 2 dimensions. So, this is x axis, this is y axis, okay, and this is from 1, 2, here it is 2 and 1, 2, 3, 4, 2, 4 is this point. Now, if I is an unit vector, I is an unit vector along x axis and j is an unit vector along y axis, okay. Unit vector means this will come as I and till here it is 2I, it will come as 2I, okay, and j is here 2j, 3j, 4j. So, this part will be 4j, here it is 2I and 4j. Now, this point is given by vector 2I plus 4j. Here you will get 2I and this is 4j. So, this point P is represented by vector, suppose it is R bar, then R bar is same as 2 times I plus 4 times j. So, this I had taken an example. See, the component of a vector I am taking in 2 dimension, component of a vector in 2 dimension. Let I be a unit vector along x axis. This I cap unit vector is always denoted by I cap, on the top of that cap is there, and j is a unit vector along y axis, okay. Then point P x comma y in space, here it is in 2 dimension and O is the origin. O is the origin here. I is the unit vector. J is the unit vector. Then from O to P. O to P is same as O to Q and Q to P here. This one is Q here. Okay. O to P is same as O to Q plus Q to P. So, this is along x axis. So, you will get x times I, here x times I, and this is along y axis. So, you will get y times j. So, any vector OP in space in 2 dimension can be represented by x into I plus y into j. Now, in 3 dimension, see the previous example here, in 3 dimension you will get x, y and z axis. So, I had drawn here z axis, x axis, y axis and this is z axis. Okay. Now, k is an unit vector along z axis, k is an unit vector along z axis. Now, suppose this unit here on z axis is 5. So, 5 is added here, 5 times k you will get vector r bar. Okay, that is OP, another name for OP is r bar, is 2 times I, 4 times j, and you will get one more coordinate will add here, z coordinate. So, 5. So, you will get 2I, 4j and 5k if any number is here in the space. Suppose this fan is there whose x coordinate is 2, 4, 5, then it can be represented by vector as 2 times I, 4 times j plus 5 times k. Component of a vector in 3 dimension. You had seen the example. Now see, this is x axis, y axis and z axis. I, j, k are 3 unit vectors here. Okay. P, x, y, z. Suppose P is here, x, y, z is any point in the space, and position vector of point P with reference to the origin, this is origin here, okay, and point P is here, then the vector OP from O to P, vector OP is given by x times I is a unit vector, y times j and z times k. So, I, j, k are unit vectors along x, y and z axis respectively. Next very important thing, see I had taken here only origin here and the point P, okay, origin and point P. In the previous example here, see this was O and here it is P. So, vector OP I separated from here, okay, O is the origin and P is here. And r bar, this vector is denoted by r bar, then this vector is r bar is given by x times I plus y times j plus z times k. Any vector in a space can be denoted by like this, x coordinate of that vector times the unit vector plus y coordinate of that vector into unit vector plus z coordinate of that vector into unit vector. So, the position vector of a point is denoted by this when it starts from origin to any point P in the space. Representation of vectors in terms of position vector of its end points. Now, P is one point and Q is another point. Now, vector PQ, how it is represented? Vector PQ is same as from P to Q, see here, it's same as O to P here and O to Q is there, okay. So, by triangle law, see here how it is written, O to P is from here to here and O to Q is from here to here. So, you will get this opposite, okay, from here to here, and that is why you are getting minus sign here, it is not going properly as a triangle law. So, P is minus here from here to here, then from here to here the direction are not same, that is why you are getting Q minus P, okay. So, any vector in space PQ is represented by Q minus P. I will explain this one more time, see here. See vector P to Q, we had seen vector P to Q, okay. vector is moving from point P to Q. So, it is same as P to O and O to Q. P to O and O to Q. This is triangle law of vector addition. Now, if I want to write this ulta O to P, I have to change the sign. Negative of a vector, magnitude is same. I want to change the direction from P to O, I want to go ulta O to P. So, I will get minus. When I change this, I have to write minus sign, and this is same. Now, the position vector of this, we had seen that point is P, small p. Now, note that this is capital P and this is small p it is. Okay. So, this is denoted by P, and this vector OQ is denoted by small q, like this. O, whenever it starts with O and ending with Q, capital Q, we are writing small q. So, this vector is Q. Now, you can write this as Q minus P. So, whenever vector is there PQ, we write as small q minus small p. Now, ST, see here, I am giving one example here, ST Sachin Tendulkar suppose. So, T is there. So, you have to write this T small t, okay, small t, Tendulkar minus Sachin, like this it is. Okay. Now, LM, Lata Mangeshkar. Okay. So, you can write this as Mangeshkar, small letter on the top of that vector, and Lata like this, small letter, like this it is. Virat Kohli. So, you write Virat Kohli. So, K will come first, small k will come, minus Virat, like this it is. This part is clear to you all. Any vector can be represented by like this, the initial point and terminal point. Terminal point will come first and the initial point will come afterwards, minus the terminal point minus the initial point. See, that is why the representation of vector in terms of its position vector, these are called position vector. When it starts with origin, it is called position vector. So, any vector PQ is represented by Q minus P, small q minus small p. So, always it is represented by this way. Vector joining two points. Okay. Now, we have seen that point PQ, vector PQ is represented by Q minus P. Okay. Now, point P is suppose x1, y1, z1, point Q is x2, y2, z2, point Q is x2, y2, z2. Then how to represent a vector? How to represent a vector? It is x2 minus x1, x2 minus x1 I cap plus y2 minus y1, y2 minus y1 j cap, and z2 minus z1 k cap. Now, suppose these two fans are there in this room. Okay. So, one fan is here, another fan is here, and you know the coordinate of this fan, okay, x comma y comma z, x1, y1, z1, and the coordinate of another fan is this. Then you have to subtract the x coordinate, then you have to subtract the y coordinate, then you have to subtract the z coordinate, and you have to write here in between plus sign, and you have to write the unit vector I, j and k. Now, the length, suppose I told you all these are the two fans here. Okay. The distance between these two can be found using the distance formula which was there in 11th standard 3-dimensional geometry. So, x2 minus x1 the whole square you have to write, plus y2 minus y1 the whole square, and z2 minus z1 the whole square under the root sign. The distance will be always positive, and that is called also the magnitude of vector PQ. The magnitude of vector PQ is found by this formula. Addition of two vectors. How to add two vectors? Now, see this two vectors are there. Okay, this is shown in 2 dimension. Okay, A1 and A2, and here it is B1 and B2, this point here. Okay, how to add two vectors? So, A1 is one vector here, in 3 dimension it is written, B bar is another vector in 3 dimension. How to add these two vectors? A1 plus B1, add the I component of this here, I terms you add, A1 plus B1, here A1 plus B1 I, then you add A2 plus B2 here J, and here A3 plus B3 and K here. Okay, so this is the addition of two vectors. Subtraction of two vectors, same way it's very easy. Subtraction of two vectors, just subtract A1 minus B1 like how you added previously. Same way you subtract here, in place of plus, minus sign will be there. A1 minus B1 I cap, that is a unit vector, then A2 minus B2 J cap, and then A3 minus B3 K cap. So these two vectors are subtracted in this way. Equality of two vectors. Two vectors are said to be equal. Vector A bar and B bar are said to be equal if and only if, see here I is there, here also I is there. This the neighbor of I, who is the neighbor of I here, A1, and neighbor of I is B1. Both are same, both these neighbors are same. Two vectors are said to be equal if, see here A1, that is a neighbor of I, and here neighbor of I is B1, both are equal. The scalar component of these two vectors, that is A1 B1 is equal, then A2 B2 both are equal, and A3 and B3 are equal, then these two vectors are said to be equal vectors. Now this is represented in mathematical form. Otherwise I had explained you all when two vectors are said to be equal. It has same magnitude and same direction, then the two vectors are said to be equal. Like this, it is the same direction and same magnitude, then two vectors are said to be equal. Now in mathematical way, if these two are equal, these two are equal, and these two are equal, then two vectors are said to be equal. Two vectors are collinear. If they are collinear, okay, now see these two vectors are collinear, then or these two vectors are collinear here, see these two vectors are collinear. If one vector is expressed as a lambda times another vector, one vector is expressed as lambda times another vector. So copy the first vector as it is only, lambda times this another vector. When you multiply this by lambda, you compare the coefficient of I both the side, and you will get this everything equals to lambda. You will get that B1 upon A1 is same as B2 upon A2 is same as B3 upon A3. So if two vectors are collinear, then this their ratios B1 upon A1, these are proportional, B1 upon A1, B2 upon A2 and B3 upon A3, all these are proportional if two vectors are collinear or parallel. Now direction ratios of any two vectors. Now see here, this is a point in space 3, 4, 5, this is the origin, okay, and this is vector OR starting from O. Then these numbers 3, 4 and 5, these numbers, the coordinate of that point, if it is starting from origin, okay, then OR will be 3i, 4j and 5k. These numbers are called direction ratios. Similarly here, see here, 2, 3, 5, this is a point in space, then these numbers 2, 3 and 5 are called direction ratios of that vector. Now see, this is a vector given in the form 3i, 4j and minus 6k, then the coefficient of this I, that is 3 here, then coefficient of j, that is 4 and minus 6, these are called direction ratios, these are called direction ratios. And when you take the magnitude of this vector, that is 3 square, 4 square and 6 square, okay, so you will get root of 61. If you, when you divide these direction ratios by the magnitude, these are the direction ratios are divided by the magnitude, then it is called direction cosine. Similarly here, see one more example, this is a vector, I, neighbor of I is 3 and j is missing here, so coefficient of j is 0 and here coefficient of k is minus 4, then 3, 0 and minus 4 are called direction cosines. When you take the magnitude of this, you will get 5. When you divide by that 5 with the direction ratios divided by 5, these are called direction cosine. So what are direction ratios? If the vector is given in this form, this coefficient here 3, 4 and minus 6, they are called direction ratios. When you take the magnitude of this and divide by that magnitude, then it is called direction cosine. See what is direction cosine. If a line, this line makes an angle alpha, this line, black line makes an angle alpha with x-axis, and this line makes an angle beta with y-axis, and gamma with z-axis. A line makes an angle or a vector makes an angle alpha with x-axis, beta with y-axis and gamma with z-axis. Then cos alpha, cos beta and cos gamma, cos alpha, cos beta and cos gamma are called direction cosine of this vector. This is clear to you all? This cos alpha, cos beta and cos gamma are called direction cosine of this vector. So direction cosine are also denoted by L, M and N also. Section formula. There are two formulas, section formula, internal division formula. See here, this is a vector here, okay, and R divides this vector internally in the ratio m:n. See, this is vector and O is the origin, okay. Now position vector of this point P, point Q is given by vector B bar. Position vector of point P is A bar and position vector of point R is given by small r bar, okay, and R divides the vector in the ratio m:n. Then the vector r bar is given by, see here, m times b bar, here m times b bar plus, when it is internal division formula, plus sign will come, and n times a bar divided by m plus n. So this is internal division formula. How to find the coordinate of a point? When the ratio is given, the ratio in which this point divides this segment, this vector, that is given, then this is the formula you have to write. External division formula. Now see here, in external division formula, R divides segment PQ in the ratio m:n. Have you seen that R is outside, not inside this vector? It is outside. R divides externally, it is outside. Then the coordinate of that point, the same formula, but in between minus sign will come. So you will get m times b bar, minus because it is external, n times a bar divided by m minus n. For external division formula you will get minus sign. For internal division formula here you will get plus sign. So same formula, but here it is R divides internally. In the next slide, R divides externally, R is outside. Product of two vectors. Now how to multiply two vectors? See here, product of two vectors, vector A bar is given by 2i plus 3j plus 4k and vector B bar is given by 3i plus 2j plus k. Now how to multiply product, this is called dot product, okay, or it is called scalar product. Why it is called scalar product? Because when you simplify this you will get a scalar answer, it is not a vector, that is why it is called scalar product. Now how to multiply these two vectors? You have to multiply 2 with 3, 2 3s are 6. Then 3 2s are 6 and 4 into 1, that is 4, and you add this, you will get a single number here, that this number is a scalar number, that is why it is called dot product, because this is a dot here, and because the answer is scalar, it is called scalar or dot product. Now the formula to find this, dot B is AB cos theta, AB cos theta, magnitude of A into magnitude of B and cos theta. Now we know that I and J are two unit vectors along x and y axis respectively. Then I dot I, put here I and I dot I will be I, then magnitude of I and the angle between I and I. See here, this is x and y axis, okay. I is a unit vector, I is a unit vector along x axis, okay. This is a unit vector along x axis. I dot I, both are on x axis only. The angle between this, suppose this is a unit vector along x axis. What is the angle between I and I? Angle between this and this will be 0. So you will get I dot I will be magnitude of I, then magnitude of I, and the angle is 0. So cos 0. Cos 0 is 1, magnitude of I, because it is a unit vector, magnitude is 1, here also 1, and cos 0 is 1. So you will get I dot I is 1. Similarly, J dot J will be 1 and K dot K will also equals to 1. Now we will see what is I dot J. So I and J, these are the two axes, x axis and y axis. Now I is a unit vector along x axis. This is I along x axis and J is a unit vector along y axis. What is the angle between this? 90, no? I is a unit vector along x axis and J is a unit vector along y axis. So the angle between this is 90, cos 90. So you will get here I dot J, magnitude of I, J and cos 90. Cos 90 is 0. So 0 into anything you will get 0. Similar I dot J, J dot K and K dot I will be equals to 0. If A bar and B bar are two vectors, okay, A bar and B bar, these are two vectors, okay. Dot product or scalar product of these two vectors is magnitude of A into magnitude of B, and theta is an angle between these two vectors, okay. So cos theta, it is cos theta. Okay, so the dot product formula is A dot B equals to magnitude of A, magnitude of B and cos theta, where theta is an angle between A and B and theta lies between, see here, 0 to pi, including 0 and pi. See this angle here like this. So it lies between 0, this angle is 0 until pi it is. So here it is, theta is an angle between these two vectors. This side vector B and vector A, then A dot B is AB cos theta. Now the properties of scalar product. Now when I had shown you all example here, we are getting the answer as a real number. The final answer when we take the dot product, it is a real number. So A dot B is a real number. It is a real number. Now A dot B is 0 if and only if A and B are perpendicular to each other. Dot product is 0 if the vectors are perpendicular to each other. So vector A is here and B is here. If they are perpendicular, cos 90 it is, and cos 90 is 0. That's why when two vectors are perpendicular, the dot product is 0. Two vectors are perpendicular, the dot product is 0. Now A dot A, you will get here, A dot A will be magnitude of A and the angle between A and A is 0, cos 0 is 1. So you will get magnitude of A the whole square. A dot A is magnitude of A the whole square. Okay. When theta equals to pi, in place of this you put pi here, cos pi is minus. So A dot B is minus of this magnitude of A and B, because cos pi is minus 1. Okay. Now just now we had seen that I dot I is 1, J dot J is 1 and K dot product of this is 1. But I dot J is 0 because they are perpendicular. Vector I and J are perpendicular. Vector I is along x axis and vector j is along y-axis. They are perpendicular, that's why the dot product is 0. Now from the definition of this, A dot B is same as magnitude of A and A into magnitude of B into cos theta. Bring both this below this, then you will get the value of cos theta. Cos theta is dot product of A and B. The angle between two vectors is taken by this formula A dot B, then magnitude of A and magnitude of B. Now the scalar product is commutative. See here, if you multiply 2 into 3 or it is B dot A, you will multiply 3 into 2. So A dot B we are multiplying 2 and 3. For B dot A we are multiplying 3 into 2, that is 6. Then here 2 into 3 again 6 and 1 into 4 again this. The answer will be same, 16 only. So the dot product is commutative. Dot product is commutative. All these are properties of dot product. So if the vector is given like this, second vector B bar is this. To find dot product, you have to multiply A1, B1 plus A2, B2 plus A3, B3 and you will get a real number. That's why it is called scalar product or dot product. Now the application of this, the projection of a vector on a line. The projection of vector, this A bar is projection on this vector B bar and it is given by A dot B upon magnitude of B. Projection of this on this, you will get A dot B upon magnitude of B and it is also given by this formula. If it was projection of B bar on A bar, it would have been changed. A dot B then B dot A, both are same, but in place of B you will get A and in place of A you will get B and angle will remain same. So this is projection of this vector on this vector. So see here, this is a line and this is A bar. So this is a projection on this vector. The projection, it has application in our daily life also. Many times we see this type of projection in our houses and all. So projection of vector on a line. Next is vector cross product of two vectors. Now vector cross product, see here, two vectors A bar and B bar. This is one vector A bar and B bar. Now A cross B is a third vector, this vector perpendicular to both A and B. So what is a cross product? Cross product is a third vector perpendicular to vector A bar and perpendicular to B bar also. And the angle between these two vectors is theta here. So the direction is very, very important. A is here, B is here, then A cross B is like this. Then B cross A you will get like this. So the direction is very important in cross product. See here, vector A cross B. A cross, here it is A cross B is in this direction. And B cross A, it is down below. The direction is this side. For A cross B, the direction is on the top. Now A cross B is given as AB sin theta and the direction is important, but this is given as a magnitude, so direction is gone here. So direction is very, very important in cross product. So here because it is taken modulus, the direction is taken out. And theta lies in the angle 0 to 180. The theta can be, this theta can be from 0 to 180, 0 to 180. This theta lies between 0 to 180. Now in right hand rule, see this is a thumb. Thumb is taken right hand of this. The thumb is taken as A cross B. The index finger here, this is the index finger is taken as vector A and this finger, middle finger is taken as vector B. So A cross B is this thumb, this third vector. See all these three are perpendicular. Okay, this side and this, all three are perpendicular and this thumb is perpendicular to both the vectors here. Okay, if you do like this also, the thumb will be perpendicular to vector A bar and B bar. Now the definition of this, see, vector A is given by this and vector B is given by this are two vectors in 3-dimensional space. The cross product of these two vectors A cross B. Now it is called a cross product or vector product because the final answer will be a vector, not a scalar. Now how to find this? See here, first you have to write here I, J and K, and this is a determinant. You have to write a determinant. Forget about the I thing, and then you take this A2, B2 here, A2, B2, then A3, B3. Okay. The second, for the second one, J part, you do not take A2, B2, the remaining part you take and take the determinant. In the K, you do not take A3, B3 and take as a determinant. Now, how to simplify this? It's this way, you have to multiply A2, B3 and B2, A3. Similarly here, both you are supposed to multiply, and here also I will show you all this with an example. So this is written as, a cross product is written as a determinant of I, J and K. Then this coefficient you write of vector A, that is A1, A2, A3, you write as a second row, and B1, B2 and B3 you write as a third row, and then you simplify. After that you will get this then. So the cross, while simplification you have to write as a determinant. Okay. So see here, this is A, this is B, and this angle between this is theta. So A cross B is a vector perpendicular to A bar and vector B bar. Okay. So same way here, right hand rule. See, I had shown you all A cross B here. These are the two vectors. A cross B is this way. Okay. This is A cross B, and B cross A is this way. Both are not same. A cross B, the direction it is moving this way, A cross B, and B cross A is this way. So not equal. It is not commutative. Dot product is commutative. This is not commutative. B cross A and A cross B, how they are related? They are minus of each other. If you want to equate both, then you have to write minus sign. So both are not commutative, whereas the dot product is commutative. Now the application of this cross product is, what is the use of this? We can find the area of parallelogram. The area of parallelogram, if we find this vector A is here and B here, A cross B, and find the vector A cross B and find the magnitude of that vector, and that is called the area of parallelogram. Now see here, I will show you all, this is a parallelogram. If I want to find the area of this, and this is vector A bar is in this direction, okay, and vector B bar is in this direction like this. Okay. So the cross product of this, the cross product A cross B will come like this. You will get one more vector cross product of this. See there, this vector cross product is going up this way. Then take the magnitude of that, and that is the area of parallelogram. Now the area of triangle, have you all seen any time that this is a parallelogram, and if I do like this, I divided this parallelogram into two parts, okay, equal parts, and I got a triangle. So area of triangle is half of the area of parallelogram. Even you can do like this also, area of triangle this way, half the area of parallelogram. Okay. So the parallelogram is nothing but it is a combination of two triangle like this, or it can be like this also. Okay. So area of parallelogram and area of triangle, they are related. How they are related, you understood? So this is double of this, you will get a parallelogram. See, there are two vectors here. I have taken two vectors. Vector A bar is given by this and vector B bar is given by this 3i plus 2j plus k. Now when we take the dot product, we are multiplying like this and we are getting a scalar answer. Now in cross product, we have to take the determinant. This is called a determinant. This is a method to find determinant. First you write the coefficient, the unit vector along x, y and z axis, that is I cap, j cap and k cap. Then you write these numbers 2, 3 and 4. These numbers are also called direction ratios. These are the numbers in the space 2, 3, 4 with reference to the origin. They are also called direction ratios. Now 2, 3 and 4 you write like this in the second row, and this 3, 2 and 1 you write in the third row. Now how to simplify this determinant? How to simplify this determinant? See here, first you write I, you copy I here, then you write the bracket like this. Okay. The second one, when you are writing j, you change the sign. Always you have to change the sign. Whichever number is here, you have, suppose it is minus, you write plus. If it is plus, you write minus. The element in the first row and the second column, you have to change the sign in case of determinant. Then the third one you copy as it is only. Now in between you write like this bracket, you write here also and here also, and in between you write minus sign, minus sign, minus sign. Now how to simplify this? Here close this and you close this. Close this first row and the first column. And what is left here? 3 and 1, multiply 3 and 1. So 3 minus multiply this 4 2s are 8. Okay. So 3 minus 8 you will get minus 5i. Then you close this one and you multiply like this 2 into 1, 2 into 1 that is 2 and 4 3s are 12. Now you subtract this, you will get minus 10 and this minus will be 10j. Now you close this one and you multiply, close this and you multiply 2 into 2, 4 and 3 3s are 9, in between minus sign. So 4 minus 9 you will get minus 5. So you will get a vector. When you take the cross product, you will get a vector. That's why this is called vector product, because the answer is coming as a vector. In this case the answer was scalar, that's why it is called scalar dot product and vector cross product. This part is clear to you all? Okay. Now see, this is a cross product. Now I had told you the application of cross product, it is the area of parallelogram. So if you take the modulus of this, the modulus of this will be minus 5 the whole square, 10 the whole square plus minus 5 the whole square. When you simplify this, you will get one answer, and this is the area of parallelogram whose adjacent sides are vector a bar and b bar. Like this you will get a parallelogram, and this is the area of parallelogram. If you divide this area by half, so you want the area of triangle, then you divide area of triangle will be half the area of parallelogram, half the area of parallelogram. So if you divide this area by half, you will get area of parallelogram. See, vector or cross product. See, this vector product, when you take A cross B, it is a vector. Final answer you will get as a vector, not a scalar number. You are getting in terms of ijk, that's why it is called vector. Now when the angle, when two vectors are parallel, the angle between them is 0. So you will get sin theta is 0. When sin theta is 0, the cross product is 0. Similarly, A cross A will be 0 when theta equals to 0. When theta is pi, you will get sin pi, and that is also 0. So A cross minus A is also 0. When theta is pi by 2, when two vectors are perpendicular, so sin pi by 2 is 1, that is why A cross B is modulus of A into modulus of B. Now I cross I, the angle between I and I is 0, therefore sin 0 is 0, that is why you are getting I cross I is 0, J cross J is 0, K cross K is 0. Now I cross J, I and J are the unit vector along x axis and y axis, and I cross J will be a vector which is perpendicular to both. Suppose I is here and J is on another x axis, y axis, I cross J will be K, like this. Similarly, J cross K will be I and K cross I will be J, because these three vectors are perpendicular to each other. Now there is a method to remember this here. I cross J will be K. J cross K will be I and K cross I will be J. If you go in a reverse direction, K cross J will be minus I, J cross I will be minus K. So, if you change the direction, you will get minus sign, but I cross J is K. Now, from the definition of this, sin theta is modulus of A cross B upon modulus of A and B. Then I had explained you all that vector cross product is not commutative. If you are writing both equal, then they differ in sign. So, A cross B equals to minus B cross A.
Prudent Scholars, powered by Lupin Pharmaceuticals.